Everything is here. Okay. All right. So, very good. We're going to talk about structure detection today. That should be the whole plan, I think, right, for this little ceremony of 2 lectures we have. Then, don't explode. Then after that, we have, so next week, this is where we are now, structure detection, pretty slides. And because, it's just, this is how we make beautiful pictures of networks. But it's good stuff. Right, so organizations would be next week, and chaotic contagion. So we'll see how those two go. There's some extra fun things at the end. They're pretty crazy. A chaotic contagion is really nuts. Okay, so this is good. We're going to talk about structure detection. All right, so there's a bunch of stuff here. This is an enormous field. It's just, it's important. It's kind of easy to, not easy, but it's something that people are good at making up new things in. There's some historical work that matters, but physicists kind of came along and started doing new things as well, rediscovering some old techniques, but making up some new ones. So, right, computer scientists have been thinking about this for a while. And of course, the whole data story keeps growing and growing, becomes harder and harder and harder. So we're dealing with these bigger and bigger data sets. All right. So what I'm going to do is give you a little bit of historical stuff again, some of the earlier thinking, which is still important. We'll get very quickly to the sort of the most famous kind of way of doing this. Actually, there's a funny connection. But anyway, we'll get to that. And then some funny ones. So there's a spectral method, so there's going to be some eigenvalue stuff, eigenvector stuff popping up, which sort of works. It's a little spooky, which is spectral, I guess. We'll have missing links. This is so this starts to say, well, okay, we're going to detect communities, and we're also going to say, maybe you're missing these links. We're going to do this so well that we'll, in fact, be able to guess which links you haven't been looking at properly, or which ones you may be measured incorrectly and they're not really there. So that's clever. Overlapping communities, so this will be a break from all of this. There's a little bit here, but the story will be, you can belong to more than one community. And this is an old point of ours and others that really sort of suggests that this is a hard thing to do, because all of these are about breaking it into specific communities. So the nodes are only in one community. Then we'll have, these I've added most recently, so I understand the least about them, but link-based communities, we've talked about links being the way to attack a lot of problems, right? Focusing on what happens with links. And this turns out to be just another perfect example. This is actually work by YY An Bagro, who's now on the team here, and Sune Lerman, who's back in Denmark. Yeah, so they're all together as a little team with Barabazi, and they did this very nice thing. They just thought, well, what about the links as communities? So that was a smart thing. And then general structure detection. All these things are kind of about hierarchies. So you've got, maybe there are 2 big groups, and then this group has 5 big groups in it, and so on, that sort of thing. So it's a partitioning into hierarchical partition, which, that's very common. That's a lot of natural systems are like that, and there are all sorts of reasons for why that's true. It's good for control and so on. And we'll talk a little bit about that with organizations. But this is a fun one. It says, well, what if the whole thing is a big ring? You need your method to actually not fail on that, right? So, but it'll do something very, very silly if it's looking for hierarchies. If it's really just a ring, it's going to fail. So that's sort of that's going to be the last piece. So, we'll sort of blend more and more into pictures as we go along. Right, so there's a classic example that I'm sure it's just sitting in Gephi. If you load up Gephi or a lot of these other systems, they'll have this one floating around. It's just 34 nodes, I think it's correct. And it's a work from 1977. Yep. There you go. So, right, it's an anthropology work. It was a study. We go and talk to all these people who are doing karate in a small club. And they don't like each other. That's what happened. There were sort of two factions, in fact, right? So that was made it an interesting thing. And there were a couple of characters who were sort of, they're kind of in between. The classic, what is it, the McCoys and who are the other ones? Feuds down south? No? Wow. Hatfields? No? Which ones? Oh, yeah, well, we can do that too, yeah. Jets, perhaps? No? Okay. Yeah. So, right, things aren't going so well. So you need to, so given this, so we turn this into an adjacency matrix, it just simply has links between them. It doesn't say plus or minus one. It doesn't say there's any antipathy. But can your method for this tiny little network pull out the two big groups? So it's become a fun little testing for people to run through. All right, so but if you have 50 billion nodes and 150 billion links, whatever it is, then how do you figure that out? You need your thing to be able to scale. And so there are some scaling problems with some of these, and that's been a bit of the battle. So there's definitely been a fight about whose method is the best over the last 10, 15 years. So as I said, certainly hierarchies is the big deal, and we'll see that that's the framing for much of this. Cliques, right? There could be little clique structures all over the place. You want to find them. Rings, it could be all sorts of things. Okay. Or it could be, for some reason, a lattice of some sort. Okay. Harder too, of course, if there are some sort of substructures there, right? There could be some clique, and then it's sort of tree-like out, right? So you don't want it to be. None of these methods really do that. I think they tend to say it's a tree, or at best, right? Or it's a ring. Okay. But you can see how you could adapt it. All right. As I said, much focus on hierarchies, rightly so. All right. So here's a paper. Santo, lovely guy. We both taught at a summer school on an island called Lipari. Maybe some of the Europeans know this, but it's off the north of Sicily, and it's extremely nice. And so the European Union has figured out that that's a good place to have a summer school every year. It's a bit accidental, actually, how it ended up there. But anyway, it's been there for a long time. It's a beautiful little island. There's Volcano is an island nearby. There's sort of some famous islands floating around, which has sulfur, just sort of. So it's I think there are about 24 kids. It's about complexity and all sorts of different kind of flavors every year. And they come from around the EU. It's a pretty good deal. So beautiful place. Anyway, so we taught together. So he's done all sorts of things, but is particularly famous now, I suppose, for this paper, community detection, because it's a review paper, right? So review papers are great things. I mean, once a field gets far enough, if you happen to be the person who writes a review paper, it's a painful thing to do, but you can end up being the one who gets all the citations. So this one is 2010, and it has something like 2,500 citations already. So it's a bit of a monster. All right. I'll cover some of. I've built my slides separately from that, but from this paper, but definitely there's some pieces in that match up. So if you really want to go deep into this, you would pull this one out. It's 100 pages long. Mm-hmm. Because it could be easily, right? So it's 100 pages long. Just go and enjoy yourself. But it's 4 years later now, so there's going to be more things. So I think the work that I'm going to shoot goes up to about at least 2010. Yeah, we'll see. All right, so there's your paper if you want to really go berserk. Okay, so the first one, which of course is the one that we won't use, hierarchy by aggregation. So this is a reasonable idea. We're going to say it's a hierarchy, right? We're going to see if there's one. And we start with, we know that when we have our network story, you imagine your little karate club data, and you've got ones and zeros in some matrix. So you start off with that. But there are 34 nodes there. So you start off without any links, just sort of take them away, and then see if we can say, well, these two are definitely in a group, and then these two are definitely in a group, and then build up like that. So that's a reasonable approach. It's a good approach. It's reasonable thinking. Turns out to not be as groovy as doing the opposite. But we'll, again, it's okay to have thought of this in the first place. All right, so you need to know how far the nodes are apart from each other. It's actually fine. You don't have to have things being explicitly networked. They could just have some, they have metadata associated with them. It could be documents, for example, and you just sort of say that they're similar in some way based on your way of combining text. So you just order them based on their distances. So, you need some, right? And then we'll just add the links in. And then this is always going to be a problem. At what point, because you could just fill the whole thing up, right? You can just go, okay, all the links are in. At some point, you have to say that's enough. And we've been getting a better and better kind of clustering story or community building thing. That sounds wrong. We use the term communities, right? So sometimes I've seen some sociologists get very confused by this. It's not communities in the sense of the sociological literature where you're talking about. It's communities of, could be protein interactions, whatever it is, right? So, but it could certainly be people as well. But it's an algorithmic thing. Okay, so words. At some point you have to say, okay, this is adding one more link is better than what we had before. Or whatever method we're doing, if it is some sort of building method, and we'll see a nice way of doing this. At some point, you have to have some criterion, some quantitative criterion that says, no, this is pretty good. And it could be that this is the optimal partition, and then maybe if you keep adding links, you get a better one, another one that's pretty good too. Like there could be that's a way to see, there are really 3 big groups, but then there are 5 groups inside this one. So that there is a really hierarchical thing. Yep. And so this term we can use in general, modularity, right? So it's modular. Maybe this is true of a system. When we get to this overlapping thing, you see it's much more complicated. But it seems that this might be generally true of links, if you focus on the links. All right. So the problem is, this is a good idea, but if you run it on real systems where you know what the modular structure are, there's just sort of proof is in the pudding problems, right? It fails. Okay. And you can kind of, and I'm going to go into some details of some of these. I'm just going to tell you some truthful stories or observations. This one, here's a little example. This I think is taken from Newman. So it's done a good job, right? It's pretty sure about these guys. But then starts to struggle with the peripheral ones. That's generally the problem with this kind of approach, and we're going to move on, but just so you have an idea. But this is an aggregation approach. All right, so it's going to fail, and this is generally hard from all of these things. It's going to fail with these ones that are kind of on the edge. So the Zachary Karate Club story, same thing. It's a tough test. All right, so here's a departure and from that approach, which very reasonable approach. Again, this is maybe a more absurd kind of way to start, but you can, I think it's also pretty reasonable. It's okay. All right, but it involves some trickiness. Okay, so some of the centrality business will pop up. Okay, so we'll go from the top down. We'll try to find the big story first, and then once we say, okay, this is a big group, then we'll start breaking that up, and then we'll start breaking that up. So that should feel like it could work too. So the question is how to do that. So one thing we'll see is this. Let me get this. Right, so if you've got, generally speaking, if you've got these big obvious clusters, and this is not easy to see because of your, this is some giant matrix you have, it's a mess. Right, if you ordered everyone properly in the matrix, you get this kind of structure. If all of these guys were listed here, and then all of these guys were listed here, and then all of these guys were listed here, and then they're listed here, and listed here, and listed here, then this would be all nice and filled in, this would be all nice and filled in. But you could just jumble this, right? That's not how it arrives to start with. So here's a general kind of problem. We'll talk about this in various ways. It's just all over the place. If you just took this and randomized it, you'd have the same density, but it'd be just everywhere. So one game is to say, okay, I'm just going to shuffle things and try to make a block diagonal thing out of it. Okay? Not the block diagonals you can get to through, You know, it's not Jordan normal form. It's not that sort of thing. You're actually just shuffling the indices because you want to, you know, shuffle them such that, okay, so this starts to get heavier around the diagonal. Okay, so this would, you know, this picture, if we line them up properly, would map to this. One thing you can see about this is that these characters in here have a high betweenness, potentially. Right? However we want to calculate it. But that's the sort of key observation. So that's how you can register them as being different. They might not have a million friends at all. They might have one, you know, 2 friends. But they have a high betweenness. So that becomes their, again, a global measure, right? A hard measure to get at. Although, of course, we walk through the algorithm of how to do it. But I mean, it's not something we've known about for 1,000 years. Okay. All right. Okay. And so the second line is, we want to find these clumps that have, and so we can quantify this a little more as we go on. They need to have more internal links than external. This is if we really want this to work, right? Because there are really only these 2 links between these big groups, and there are tons of nodes in here, and they have all this nice, it's a rich community, right? Then internally, there are many more links than you would expect if everyone was randomly wired up, right? So if you take this and randomize, right? So the whole thing when we break them off into little stubs like this, that whole business, randomize the whole thing, then it's just going to be a big hairball, right? Look. Okay? You'll never get this back. This is a very unrandom situation. No matter how random the internal parts are, this is a very low entropy state, relatively. So one thing that's going on here is if we said, okay, if we really could find this partition of this group, this group, and this group, we could see that the number of links on the inside of this thing is much higher than you would expect if they were randomly wired up. So the internal links to this group, the internal links, and then these cross links, which is to say it looks like this, basically. Nice and dense, nice and dense, nice and dense, and then sparser out here. Okay. So these are going to be modules, and then you could have, right, modules inside of modules. So this is all good if it's nice and hierarchical, which may not be the case. Okay. So this is the plan. The plan. All right. So Newman pops up once again. There are actually a lot of people involved here, but you know, Newman has to have done something right. So, and Michel Gervin, who was in one of my recitation classes at MIT in probably 1996 in differential equations, 1803, I think. So that was funny. She, she's one of my students, crazy students. And then, she went to Santa Fe, and they did this night. There were a couple of papers on this stuff. One was in PNAS, I think, and then this one in PRE, that I think had 4,000 citations each. It's a field that just loves to be a field. You know, it's just going berserk. It matters. You know, you can see why NSA would be interested in this, marketers would be interested in this, political scientists, political, activists, and so on. All right. Scientists should be interested in this because that's how you can figure out what's actually going on. All right. Okay, so more papers, if you want to go and read some more while you're enjoying your 100-page paper. There are many, so they've done a lot. I'm just going to give you a few here. So this is the PNAS one. So it's actually 2002, but this seems to be a more solid piece here in terms of, analytic things for you to enjoy. All right. Okay, so it's this picture I drew. The idea is that the betweenness of characters who are adjacent, right? So these ones here, here, and here, the ones that carry the connections between the groups, simply have a higher betweenness. So the game might be, okay, let's build it up by division. We'll start deleting nodes. So instead of starting with the nodes and adding edges, we're going to delete nodes. And we could delete edges. That might be another way to do it, like take their edge away, right? And see. So if we do that iteratively, and we take away the most important edges, we should end up with groups, right? All right. You know? And I'll say this again, but there's an interesting little problem that could occur, right? So this, in terms of shortest paths, it could be that, say, for example, this one takes all of the shortest paths, and this one doesn't. It looks like it probably doesn't. I mean, these are the two connections between these two communities. This one might have sort of 0 betweenness. I mean, or just 1, right? Not much. And this, essentially, all of the paths that follow the shortest paths from here to here get carried along this edge. So that's got a high betweenness. So if you're going to do this deletion thing, you take that guy out first, and then you look at the betweenness levels of the rest of these edges. This one's going to be very, very low. So you have to actually recompute the betweenness every time, because once you take this one out, suddenly this one's going to get, it's very much like an electrical circuit or a road system, right? You get rid of one bridge, then the other bridge is going to be, even if it had no traffic to start with, suddenly it's going to be the bridge that everyone wants to go on, right? Okay, so that makes sense? All right, so, but also, it's clearly computationally burdensome, which is a problem for majority of these methods. All right. Okay, yeah, it's edge-based. I was talking about nodes, but it's edges. Okay, so you find the edge betweenness for the whole thing, which we figured out how to do that the other day. It's not too bad, but it takes some work. So we're going to take away the edge with the highest betweenness, and then you have to do everything again. There's no... It's funny, you might think that you might be able to just incrementally do it, but I'm guessing you kind of have to redo everything. All right. And then you just keep going until edges are removed, right? So you've got this network that's being degraded, and then you want to look at how this network gets degraded throughout. Okay. So let's say you start with a network, it's just one component, there's one component in the whole thing. You don't have separate pieces. So you've got this number of edges removed, right? So it starts from 0, goes down to the total number of edges, and then you record at what point the thing splits into 2, because it will split into 2, and then 3, one of those components splits into 2, and so on, and you'll get a dendrogram, right? What typically called a dendrogram. And it'll have this, so there's an index here, which is the number of edges removed, so it's just linear. Play around with that, but it's just linear. And the idea is here it's split into 2 big groups, and then that group split into 2, right? And then this one split into 2, and that kept going until we're down and there are no edges left and everyone's their own little group. So this is some version of the communities. Everyone's an island, right? Yeah. And there's the version up here where it's just one big blob, in the sense that there are no disconnections of communities. There aren't any separated off. Right? This is still one big blob. You can get from everywhere to everywhere else. But as soon as you get to this, now you've got 3. And this dashed line will, as I said, we'll get to some measure of, at what point you decide this is a good, you've done a good job. So, the idea here is that there's some measure you're computing along here, which might seem similar to some other problem that we're working on for some of you. So this notion here is that there are 4 groups. There are 4 groups that maximize some measure of goodness of community structure, or modularity, right? And the term we'll use is modularity. Okay, so we're going to dive into some madness here. All right, so as I said, you have to recompute betweenness. So it's a bit arduous. You have to do it because of this reason. Right, so an edge that might have low betweenness at the very start, take away one edge and suddenly it's got a giant amount of flow on it. Flow, all right, so when do we stop, right? How do we know that our divisions are, this is a strong word, meaningful? So we're going to introduce a modularity measure. Oh, right, yes, so we interrupt this program to bring you a better explanation. Okay, so here's an explanation of one measure of modularity introduced by Newman a while back. Okay, so let's imagine we have a network and we've decided that there are 3 communities here, or we've made a guess that there are. So some nodes have been grouped into
communities 1, 2, and 3. There are some edges between each of these groups, and then many edges in within. And so that's what we're aiming for, right? We want more. If it's a real community, we should be able to see more edges within, right? So there are more ways to do this later on, but this is a good start. Okay, so all right, let's go through. We count up all the edges. We have so many edges, and we then create this matrix based on the community structure we've guessed at or arrived at through some algorithm. And so each entry is the fraction of edges between community I and j, and it's symmetric, so these things are the same, right? So we're just going back and forth, and that can lead to some problems, but that's just the way this is. So it's a symmetric matrix. So E11 is the number of the fraction of edges, right? So look at all edges and take the fraction between nodes in community 1. All right, so if we sum, okay, here we're summing across, it doesn't matter, but if we're summing across, so j equals 1, so we're summing across here, then we'll call this thing AI. So this is the fraction of edges that have at least one end in community I. All right, so that's a good thing to know. So once we start to then think about a random version of this, right, we always want to compare to a random version, and many of the things we do, then we'll need to kind of understand sort of the degree of these things. All right, so that little guy there. So the randomized version, then we'll build it. We can at least write down how the edges would be distributed. So Eij random is now going to be AI times Aj, right? So this is the fraction of edges coming out of community I, community J. We just multiply those two guys together. So these are, so now it's independent, right? It's been separated. We can just check that this is okay. So if we sum over J again for this random version, the AI is independent of J, so that pops out. Sum of this guy, we get 1, right? So we've got AI again. So it looks the same in terms of the fraction of edges that are within, or that have at least one end in a community. Looks the same. It's independent, so it's a randomized version. All right, so that's useful. So one thing we can then say is, well, what's the fraction of edges that are completely within communities? And that by itself is not enough, right? So we could just have one big network, or we could just put a big circle around the whole network, and then all of the edges are within the community. So that would get a 1, right? If we just measure that. So we want to subtract off what we'd see if what we'd find if we randomized the system, right? So we're going to keep these same groupings. The same number of edges are going to be related to 1 and 2 and 3. We're just going to randomly rewire them. So if we've done a really bad job, it's going to be very dense here, very dense here, very dense here, and very few edges in between. All right. Okay, so what we're getting to is this. The fraction of edges within communities is going to be actually the trace of each. So it's a sum of EII, right? Right, so we're going to sum down here. So that's the fraction of all edges that are within communities. And then we have to subtract off the randomized version. And Eij random is AIAJ, so we want AI squared, in fact, right? So this is the sum here. So this is what EII looks like, right? So this is EII random. So we subtract that off, and so we get, so if this is, and then we can play around with this, right? So if it's 0, of course, then we haven't done a very good job because we're at the same level as a purely random version. But we want to see this thing to be positive, right? So we'll have that later on. So this is simply the trace of E. This guy, we've seen this before. So it's sum of I. So each one we can write like this. Let's write as J, E, right? Ij. That's the first guy. And let's make it a K, EIK here. Yeah. And I'm going to put this guy, this sum in. Pull these guys out, swap one of these guys around, so let's, because of symmetry, we'll write this as EJI. Okay, so we've got a sum for J, sum for K here, and the sum of I is here, and then there's an EJI and EIK, just delicious. So these guys match up, and this piece here is the ijth entry in E squared. right? This is the definition of matrix multiplication, row, column. And then, sorry, that's the jkth entry, right? jkth entry. So, and then it's the sum over j and k, so that means it's actually the sum of all of the entries. So it's what we might call the 1 norm of e squared. Right, so you compute e squared and then just sum up all the entries. Okay, so that's a nice way of representing that, and that is, arguably the simple, one of the simplest measures of modularity.
Okay, here's a little test case. Just see how this thing works. So, 4 communities, 32 nodes in each, and it's going to be random except for one aspect, right? So the average degree within groups will be 6, and the average degree outside of groups will be 2. So on average, everyone has 8 friends. I think that's right, 8 friends, but 6 of them on average will be inside your community. 2 will be outside. All right, so that's, should have strong communities. You should be able to find it. So this is exactly that same picture again. You're developing this dendrogram by taking the network, computing the betweenness for every edge, removing the edges one at a time, recomputing. And the modularity score is maximized here very early on, and it is for these 1, 2, 3, 4 groupings. And you see that when it's partitioned eventually, these were the original 4 groups. Okay, so it's a start. I mean, obviously, it's completely concocted. Yeah. Yeah, I must have miswritten that. Okay. So is that okay? All right. So that's good. Yeah, so it looks like you could potentially get excited about further structure in here, right? Because it keeps going. It's remorseless. But you can see it is decreasing. I mean, possibly you could get another little peak in there, right? If there was an internal structure, maybe it would do that. But there's a clear automatic way here of stopping. All right, so this paper then goes on to tackle all sorts of actual networks, and so there's a stylized example. The whole plan is set up. It does a very good job with the Karate Club. Okay, they've got to do that. They've got to test it out. And there's always this kind of issue of where these characters kind of lie. Does your method put them in the wrong box? Say they're Yankees supporters instead of Red Sox, something bad like that. Disaster. All right, so separation. Okay, this is and I'll show you some more in a little bit. Here's a funny kind of diversion. Okay, so betweenness is all about shortest paths, right? So it's very kind of smart kind of betweenness. So for each edge, the betweenness weight is going to be how many shortest paths that go across it. So that's a burdensome kind of thing, in the sense that you have, if that's really the dynamics of the network, that things really do travel in that way, then okay. But maybe they don't. Maybe it's a social network. There's nothing even travels along any of these shortest paths. So it's a bit funny. But you could imagine, well, what about some other kinds of paths? What if we relax it, right? So the worst thing would be just random walking, and we'll get to that in a funny kind of way. We'll get to random walking. But here's something which we have all the apparatus sitting around for electrical circuits, right? So we know all about these things. Yeah. And so the idea is, all right, well, let's just replace every link with a unit resistor. And we're going to take so instead of taking every pair and finding the shortest path, which is just one path, and then, right, so if we found the shortest path, of course, we did this whole thing where it could split, potentially, right? So the shortest path for this guy might be, it would be all of these, right? So you get a third traveling along here. So you put your beans, so you say, go from here to here, half a bean here, and so on, right? Right? And you get these weights adding up. Now, if we do this ridiculous thing, instead of putting beans in, we put a unit current in. So we're just pumping electrons in. And we draw it out over here, and nowhere else in the network do we do that. Then, so there's going to be flow in here and flow out here according to Kirchhoff's laws, right? You know, we could flood the system with whatever. We do all sorts of things, like mice run around. I don't know. Count how many mice, hamsters are in tubes. But so we know what it is. So we're going to do it for every start, S and T start, well, terminus perhaps. S and T, this is the first one and the last one. We'll take every pair, and for every pair you'll find a current running along one way or the other, and then add all of those currents up, and that'll be an electronic betweenness score. A little bit crazy. So electricity takes a more circuitous route, right? And it turns out, well, I'll say this, it does exactly what random walks do, right? Which is kind of weird, right? So the same mathematical result. Okay, so here's the plan. We're going to measure the current along each edge, given that start and end current situation, and then we'll sum over all of them. Given we, every pair of ST, we'll go through all of those pairs, so n choose two pairs, and I guess go either way, and then sum all of the absolute values of these things, and we'll get some betweenness, right? Electronic betweenness. So, as I said, we'll get to that. That's actually a bit of extra work, but we'll get close to it. Okay, so I think this is right. I had to change it. So the betweenness for the edge between I and J, so instead of L, we'll just say I and J, given some S and some T, where the current is going in and coming out. So you need to measure the voltage at I minus the voltage at J, right? Because it's a unit resistor, right? V equals IR is it's a unit resistor, so V is proportional or just equal to I. And then there's a 1 or a 0 based on whether they're actually connected. I guess I could make it the other way. Feels like it should be going I to J. Yeah. No biggie. All right, so that's kind of crazy. So we should be able to compute this and then add them all up. So it turns out to have some nice linear algebra properties and graph theory stuff. Okay, so we have some voltage reference, because you can always, right, there's nothing absolute about voltage. It's always relative that we worry about. Okay, so now we're just looking at a particular node. This is really silly. Now we're just going to look at a particular node. Right, so here's I. It's got some current flowing in and out. There's S and T are somewhere in the network. Right, and so there's current going in and being taken out. And being taken out here, and that's causing some flow around the whole thing. So here's node I. You have to balance everything around it. So we're going to sum from j equals 1 to n, so we're looking at all possible. We can actually include n, that's fine, because these guys are the same, so that just vanishes. So the total current, right? So this is V divided by R, which is I, so that the sum of all the currents relative to I, right? So this is all the currents going out. Yeah. We don't have to say J not equal to I, because it just gets set to 0 here. So the sum of all the currents has to be 0 in general, except when there's this little business here, right? So if I is the start one, then the net current coming out of I is 1, so it's a little Kronecker delta. And if it's the terminus, then the net current coming out of I has to be -1. Being pulled out of the circuit there. Right, so this looks like a matrix equation kind of thing. Eek. And we can play with these little guys here, but there's just sort of a vector story here. All right. So if nodes are connected, their resistance is 1, which is the same as their same as the adjacency matrix entry. Right, so we're just going to do that, which is the same as 1 over Aij. So if Aij is 0 as well, then we'll get, right, this is infinite, the resistance is infinite, so we'll get a 0 there as well. Okay, so that works out. Sorry. Yeah. I mean, there really are some crazy schemes. That's what we're going through. Lots of crazy schemes, okay? A sampling of crazy schemes. Okay, so let's look at this guy. Right, so we've replaced the 1 over resistance with Aij. Good, that's good. And then we're going to mess around with this a little bit. So, yeah, so it's Vi relative to so it's the voltage of I relative to its neighbors. Good. Yeah, okay, all right. Okay, we're going to mess around with it. Let's see what we can do with this guy. Okay, so it's a Aij, Vi, and a Vj here, right? So that's just a normal A matrix, except it's J is being summed here. Right, so that this guy goes with this guy, that's going to be all right. That's an A times a V vector. So let's get that. The first one is just Vi, that can pop out, right? That's a constant relative to this. So this is a Vi, it's the sum of J of Aij. What's that? For given I, yeah, so I is fixed. The sum of the adjacency matrix. Yeah, right, yeah. So we're going to make them, it's an undirected network, so it's just going to be just degree, good. Right. So that's just going to be degree of the ith node, and then this is a proper looking product, right? So this is going to be the adjacency matrix times the voltage vector. Cool. Right, so, yep. Agree with the ith guys, yeah? Vicky. And this, yeah, Vicky. Okay, so we want to make it look like something times Vj, and we can always do that by sneaking a little identity matrix, actually. Put that in, delta Ij. All right, good. So this is going to be a blob, and a blob, these guys can be put together, and the Vj can be put on the outside. So now we're going to get something that looks like a matrix times the vector Vj. It wasn't obvious. We had to do some sneaky things. So it actually looks like this. So it's actually the ith entry of k, right? So this is going to be the degrees along the diagonal, right? So it looks like the identity matrix with a ki, so it's weighted along the diagonal. And the adjacency matrix is here, right? Times the voltage vector, the ith entry, right? Cool. Cool. It's pretty good. All right. This is at node I. So given ST, right? So given ST, K minus A times V will give us the current flowing out of node I, right? Yeah. Sorry, it will give us a thing we can solve for voltage. What do we say? That's what we want. We want all these voltage, right? We can get the current along each edge after that. Right, so we'll get the voltage at every node, and then we can get the current. So once we get the current on each edge, then we take the modulus of it, we don't care if it's positive or negative, and then we put that in a bin, and then we change S and T, and we do it over and over again, and we sum up all of these currents. The right-hand side we'll replace with this thing, so it's going to be I external, right? It's being forced in and taken out at some point. As it's set up, it depends on S and T, and it's just the ith entry of some vector. All right, so this is what we have in general. It was the ith entry of a vector. We had the ith entry of this blob on the left. So this is the whole matrix business. So we invert it? No, we don't. Okay. It's really good, you guys. So square matrix, right? Vector, this is the thing we want. We know this, check. check, unknown, AX equals B. So this is a Laplacian, which pops up all the time in graph theory. So much excitement for the Laplacian. There are reasons for getting to it. LU decomposition, grooviness, yeah. So Newman in his paper gets upset about this a little bit. Says, well, no, it goes on to say that yes, because voltage doesn't have a fixed reference. I mean, it's all relative. This thing is, you can't solve it, right? There's going to be, you have to fix one of the voltages and then you're okay, if you like, right? You can do it like that. But if you do it, the proper linear algebra way is, okay, good, we know that. One way, okay, I'll show you how to see this, but this is just generally true. Voltage is just relative, right? So it's always going to be that there's some null space here, right? That's really the thing. Yeah. We'll always be able to add something to our voltage uniformly, such that it'll still be a good solution. Right? It's only unique if the only thing you can add to your solution is 0 and still get a solution. If you can add some vector and still get the thing to work, then that's it's trickier. Okay, so if there's one component, then you get in trouble with more than one component because you could have different voltage levels in different things. Okay, so it's connected enough that there's one component. Then the null space is one-dimensional, and in fact, you can see what it is. So the null space of this guy is just going to be any constant times the unit vector. That's your offset. Whatever solution you take, you can add anything times ones, right? A vector of ones, and that will still work. And so you can actually, and so there's a physical intuition for this, and then you can see it here though, right? So this is just the degrees on the diagonal. If you model it, right, that thing times the 1 vector, just gives us the degree vector, right? And this 1 vector it's basically a summation operator, right? In a sense, right? It's sort of, if you operate in a sense, so take a matrix, put a 1 vector on this side, and it just says sum up all the rows. That's going to be your new vector. So sum up all these rows, it's the degrees. So you're going to get 2 degree vectors, get 0. So that's cool, but you solve it with this good thing. Yeah. So you have to do that over and over again. That's kind of arduous. It's a little crazy. So the random walk between us, I mentioned it's the same thing, but this is, how it plays out, how you think about it is slightly different. This is the problem with this is the sort of the concern you might have about shortest paths, apart from the fact that it just doesn't make any sense, is that, they're hard to find. And they're sort of asking a lot of nodes to know what the shortest paths are. If they, yeah. So at the other end, perhaps, is that they have no idea what they're doing, and you let them wander around, random walkers. Yeah.
If you're doing random walks, wouldn't that eventually dissolve just down to like degree centrality? Because you'd be more likely to visit the nodes that are
Yeah. So why doesn't that? So the betweenness of the edges, yeah. The betweenness of the edges should be products of the degrees, right? Well, it's more complicated, right? So that it's degree central for the nodes, but for the edges.
Yeah, so is that enough to change it?
Yeah, when you look at the edges, it's different because the edges have. No, this is not right. The edges have uniform flow in them. Well, you're right. Okay, so here's why this is more complicated than that one. Okay, so if it's pure random walk, you have one random walker and you let them go everywhere, the edge between us you'd end up with is uniform. Actually, everyone would have the same edge between us because random walkers are equally likely to be on every edge. The difference is actually you have a source of random walkers and a sink of random walkers. That's the difference here, right? So Okay, sorry, yeah. Yeah, good, excellent question. So you're going to say, here's I and J, what's the shortest path? And then find the shortest path, and then you give a bean to each edge. And then we repeat that everywhere. The electronics between us, you put a current in here and a current out here, and then you compute. And actually, it will go everywhere, so you get a little bit for every edge. This one, you send your random walkers in here, and then they'll pop out. Yeah, pop out this one. Lemmings, anyone? It's kind of like Lemmings, the game. It's from a long time ago. No one knows Lemmings. It's tragic. It should be yes? Great game. It's never been quite. I don't know why they don't make it for like an iPad or something. There's a game called Caveman, which is basically the same. Yeah. But kind of like that, right? You have all these little guys spewing out at one end, and then they have to get into a hole at the other end. In that game, you have to kind of make that happen. But you've got a random. This is random. You've got a network, and they're going to wander around, and they're going to disappear out the hole at the end. It's going boing, 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 boing. You might have to blow a few up. It's a great game. Really a great game. Lemmings, huge. Really interesting. Okay, highly advise you play that. Okay. So, so that's the difference. It's going to be, we're going to say I and J, we're going to let them run out, and they're going to disappear once they get to J. Yeah, which is ridiculous. And then we're going to take every I and every J. And the way to cope with this will be, okay, so it ends when it gets to J, and then we record the number of times that each edge gets traversed. But they'll get traversed different numbers in different directions, right? So it's the absolute difference in the probability of random walk goes one way versus the other way. Yeah. I have to think, I'd have to check on whether that's done per pair, right? Random walks. All right. Okay, so you know the whole diffusion thing? Similar thing, right? So, which we had that little section on diffusion as well. So you can do this as well. You can think of it like this. It's the same as all things electricity. Okay, so here's a result for using the shortest path versus the random walk versus, and here's shortest path but without recomputing betweenness. So you just take the betweenness that you got at the start and then just start, and so you just one computation, and then you just order all the links by their betweenness and then just take them away. So we argued that that was a bad plan. And you can see that the modularity story, this one has two little peaks there. Well, maybe two peaks there, and this one's kind of bad, pretty bad. So this is, I think, yeah, this is Zachary's, right? This is the Zachary one. And you can see there's a miss. I mean, it's not a disaster, but this one got put in the wrong box, according to the actual original study, right? So this one got put in the wrong box here, but it's okay here. And you don't really get to a point where this has been divided up well. In fact, you see the first break-off is just one guy and everyone else, which is really not the way this should work, you know. That guy. Okay. Whereas, yeah, so these ones do a good job, both of them do a good job of breaking into two big chunks to start with, or early on. And then some structure within that. Groovy. So these sort of things are built into Gephi and whichever other evil black box you want to use, right? So you're going to call these things to work. So I think in some ways this is where we are now. You just need to know what you're using. You're probably never going to code this up, right? Unless you really want to. Okay. What's that? Yeah. Yeah, I mean, there are a lot of scripts floating around. There are certain packages for MATLAB now. There are really horrible things in R that people use. Yeah. Python will have, you'll be able to find them. Everyone fights for the, okay. I'm sure there are. I mean, I haven't used them so much, but I'm sure there are. Yeah. Poor old Python. Okay, so there are some fun ones. This one is scientists working on networks. This is in 2004, based on archive papers. And so you can see there's a big division here, lots of interconnections, so you can see there's sort of some central characters here, and so on. There's a bridge here, which is amusing. These are the big, the big components that come out. And I don't have the associated kind of division dendrogram, but this, I guess, is the best modularity. So it's quite, broken up. And so then, you can start to, we'll come to this again later on, there are links between communities as well, of course, right? So you can start to think of this as a network now of communities, which is a good plan. All right, so the actual names of humans. So so in fact, I'm in this one, which is that's me. This is because this was river networks, and then this is social networks. And so that connected across, so there's Romu Pastor Satoros is in there, Andrea Ronaldo is there, and then so this is this Italian-Spanish group. And these guys have done a mixture of kind of everything. Ikancho's worked on, these people, oh my God, there's tons of people here. A lot of stuff, a lot of fun things on language. Stauffer, very famous for percolation. Of course, it's 2004. Now it will be just completely filled. There's Luis Amaral, Portugal. He was at Northwestern. Gene Stanley is here. I mean, it's just Sid Redner. It's a crazy, crazy list. Barabazi is, where is he? He's in there. There he is. That guy. He's a hub. Hubtasticness. Right, so over on this team you have Watts, Duncan Calloway, who's at Berkeley now, Michelle Gervin, Strogatz, and Mark Newman is in there. But if we did this again, this would be ridiculously connected. And yeah, so it'll be problematically connected. Anyway, so that's fun. It's 10 years ago, yeah, at least 10 years ago. Cool. Anyway, so I was once important. Dolphins. All right, then it's just a free-for-all. It's like I have a social network of dolphins. These are the ones that are friends with each other. Let me find their communities, and then the dolphin overseers say yes, it's true. So there's a lot of good work. Les Miserables. So there's a lot of testing on things what the story is. Of course, you have to do that. And I can't remember offhand how this was done, but presumably they're in the same scene. Yeah. So look, this is one of the so-called digital humanities or distant reading, perhaps, but digital humanities stories, right? That people keep arguing about and saying it's a disaster. But it adds to literature, and it can add in very good ways and bad ways, of course. Okay, so yeah, that's fun. Okay, so there's more in there, but that's just a couple of examples. So I'll take you through another approach. How are we doing here? Let me take you through this one, then we'll have a break, and we'll go through these other. We'll go through these other methods. Okay. All right. So I think we have the basic plan, right? The battle is to find these communities which are kind of obviously there. But in some cases, they're messy and hard to see. So this is a paper that appeared in PNAS in 2007. Similar game, trying to get to a hierarchy, trying to get this thing that I was talking about before, right? Where you have a big mess and you want to shuffle things around such that the modules become self-evident, right? It's an interesting game to play. So they do, this is kind of crazy. So you've got a network and you consider every possible partition. So this is going to be computationally scary. Yeah, this thing, what's that? Yeah, it does suffer a bit when as it gets bigger. Yeah, for sure. Yeah, you start to do Monte Carlo type things. Yeah, but at least theoretically, this is going to be the idea. Every possible partition, every insane partition, right? Okay. So same idea. You're going to measure modularity. Okay, and then you're going to have a network of the partitions. So you've got your network, and then you're going to have a network of the possible partitions. And they're going to be adjacent to each other if you just by moving one node in one of these partitions, like moving one node from this team to this team, you create this partition here, then they're connected. So partitions are going to be connected to each other if they're very easy, right? You just flip one node's affiliation and you move from one to the other. So it's going to make this big network of partitions. Right, so one partition is everyone's in the same group, right? And then the partitions that are right next to that are all the partitions where one character is off by themselves and then everyone else is there. Right, you go, bloop, right? That's, yeah. So then you start to slide away from that. Yeah. Okay, so you just reassign a node. So we'll look at it exactly. This is small networks. We'll look at a small network example. So you're trying to look for, I don't like that. That's probably not right to say this. This takes a while to think about, actually. So, okay. So we have an affinity matrix. IJ, we'll call it AF for affinity. Random walkers again. So now it's going to be probably the random walker on a modularity network. So we've got this modularity network, right? The network of all partitions ends up at a partition with I and J in the same group. Right. So this matrix is going to be a measure of how often I and J are in the same group given some partition. Right. So the Zachary one. There are a couple of borderline characters, but there are some that should always be basically in the same group, right? So they'll have high affinity. So so this is repeated by others, this kind of approach. So now we'll take a whole ensemble of partitions and then just sort of take a superposition of them, which is a classic, like we're not sure what we're doing, so let's just put everything in a box and average it. Topological overlap. We'll get to that again, but we'll get to that for communities, but for I and J, it's how many of your friends are, so given your total number of friends combined, what fraction of them are the same? Right, so if you share exactly the same friends, it's 1. If they're completely distinct, it's 0. If you don't count each other, I guess. Yeah. All right, so here's a sketch of how it might work. Wow. That's the network. This is the original network. This complicated thing up here, A, B, C, D. I mean, it's brave work. This is brave work. And this is the, yeah. So here are the partitions, right? They're all in one team. This one is 2 teams, here and here. Here they're all in different teams. So so for instance here, if you flip the affiliation of this one and say, now these guys are in the same team, then there's a little arrow drawing it to this one. It goes from here to here. Why doesn't it go back the other way? Oh my God. This one, right, you flip this guy and they're in that team. Why doesn't it come back that way? Surely it would come back that way. Yeah. Yeah. I don't know. You should do it. I don't know. I mean, I would look that up and do it if no one's done it. It's kind of where we are now, for sure. It's a great idea. Why not? Stuff it into Eureka. Ask Watson. No, but that's good. Yeah, that's cool. Right. Why not? Yeah. Yeah. Write it down. Okay, so let's see. So there's a measure of modularity here. These guys aren't very modular. Oh, this is a very hard thing to think about. Why are they in different teams? This matrix over here is this is the affinity one. So what you do is you run these random walks, and they always end up here or here. Is really the story. They end up, half of them end up here, where everyone's in the same group, and half of them end up here, where they're in these. It's broken into two pieces. So yeah, I mean, it's a similar. It would be adjacent to what you want to think about. It's a landscape of partitions that somehow you run around on, and you end up in particular locations. So that's what this is. And then if you reshuffle them, reorder them, so A and C are always in the same group, which is true, right? So A and C are always in the same group here and here, and B and D are always in the same group. And then half the time, they're also in the same group as the other guys. So, you know, from this you start to build. So here's your, this is a good group. These guys have some affinity for each other, but the idea is that this is the main break for this thing. That it's two teams, this one and this one. C is you shuffle this a little. You actually have to shuffle this. You create this affinity matrix, which is so through some process you essentially, I mean, different processes you do this. You end up with how often, what fraction of the time, or what fraction of partitions that you think are decent partitions, do I and J end up in the same box, right? So you get that, and then you shuffle it to put them near each other. So we need to shuffle, yeah. Offhand, I don't quite understand this is a tough paper for sure. But the direction, you know, why you can't go back this way? It's out of my head. The basic plan. This is sort of a show and tell. Basic plan. Okay, so yeah. All right, so you get a distribution of classification hierarchies. It's not the one with the highest modularity, right? It's the one, it's according to the basin of attraction. Like if you're wandering around in partition space, which ones you end up at? They don't have to be the most modular one. Okay, yep. So given these affinities, so that's a lot of hard work to get the affinities out. Now you have to sort them. And it's a permutation of this matrix to minimize this cost. So if you look at this is really saying, okay, there's a matrix of affinities. I minus J is really just this. It's this distance. Yeah, distance from the diagonal. So it's weighting it. So the point is, the idea is you want things that have high affiliations to have small distances between them. So they should be grouped together. Right? So these guys that have high affiliations, you want them to be close to each other. Right? You want a really strong block structure. It means that these two, right, their affiliation point is out here, or their entry for their affiliation is out here. So that's actually costly for this guy. You want ones that have super affiliation to be right next to each other. Right, think about it like this. You've got Aij and then I minus J. You're summing over Ij. So you're taking your whole matrix, right? The entries AI, Ij everywhere. And then this is the weight. You could actually, put this to some power. I mean, it'd be stronger, right? Or any function of I minus j, absolute value. If it increases, if it's an increasing function, that means you're penalizing. You don't want to put a nice big fat weight out here. That's going to be the worst possible one. What do you think of this madness? The idea is you've got an ordering of the nodes here, and then you put down there some value, some score that you have, and here it's this affinity score, which is supposed to reflect how often are they in the same community, right? So to start with, that's just a scattered mess, and then you want to shuffle the order of these things to put the weights near each other. So say there are 4 big groups, like really 4 groups. Then this would be all nice and the numbers would be large in here, and these would be close to 0 out here. And the way to get to that is to say, well, let's start shuffling, and I'm going to penalize these points out here by saying they're worth their value times I minus j. So I minus j is the distance from the, right, if this is I and this is j, I minus j is the distance from the diagonal. Right, so if j is I plus 1, that's the best you can get. You've packed them right next to each other and you've ordered them right next to each other. Yeah? I'm worried about this a lot. I'll show you what we did. It's crazy. So you pack them in, and that, so even if this is a large number here, you're not being penalized by it. So if this is a 0, then you make I and j the gap between them as large as you want. Right? If they have no affinity, then you want them to be separated. How do we feel about this? Pale Sado. Should be 13 and 14 in the slides. Okay. What's that? Well, I think the problem in the end is the speed. This is a tough thing. So as I said, you could use any function as long as it's increasing. If it's increasing fast, it really penalizes things. I'll show you an odd thing that comes out, which should help but doesn't help. Okay. Okay, so you've got this horrible mess. This is their effort, so they've gone through the big, create a partitioning landscape, run around on that, find all the partitions that are most likely, create this affinity thing, and then cluster based on that. All right, these are traditional, or the standard kinds of clustering. What they're trying to show, gosh, this is really messy. These are different kinds of clustering, so it's fine. Okay. But there's a really deep modular structure in here. So this is a made-up one. They can get it out, right? So it works. 640. It's not huge. Average degree 16. Here's a little for you linear algebra fans out there. This is a funny thing. So we could make, as I said, the weight has to be just some function of I minus j. Right? The distance from the diagonal for these 2 nodes I and j. So as long as it increases. So you could have even powers of I minus j. And it turns out for I minus j to the power of 2, the rank of that thing is just 3, which is odd. So you can make the thing infinitely big, but it's got a rank of 3, which means it only has 3 non-zero eigenvalues. It's a symmetric function. It has 3 eigenvectors, which you can actually detect, which is weird. So I found this out by numerical inspection. It turns out this is the solution for the eigenvalues. It's nuts, and then actually the eigenvectors have, and they write some mad terms in here. You can see there were sums from 1 to n and sums of the squares from 1 to n. This is really nuts, and you can actually figure out what the eigenvectors look like. The eigenvectors are actually pretty well behaved, right? So here's one where it's just actually a linear thing. It's linear. This one, it's got a both of these have parabolic structures in them. Actually, as you go down through the list of entries. So you would think you could harness that for good, right? But I'm not sure. I'm not sure that you can. So T is really just this sum of 3 outer products. Right, it's a rank 3 matrix. So we can write it as this, right, just as these 3 guys here, and we know something about the structure of the eigenvectors. You'd think you might be able to speed up that search process. Yeah, okay. So that's just a little aside. They did a whole bunch of things, right? So the biggest one was 3,000 nodes. That's pretty big, 28,000 edges. I mean, you know, if the thing's going to chug to a halt, then that would be a good test. E. coli's in there. Let's have some E. coli, email interactions, and electronic circuits. All right. So, you know, they're able to have some fun with this. So you can see modular structures is for the airline network. Right. So there are these big connective pieces, and then many layers of modularity here, right? 1, 2, 3, 4, 5, even down to here. So yes, this is the whole world, and then they take this part, which is Africa, up through Asia and also Europe, and then you have these different pieces within there, and they've got this bit blown up. So, you know, that's something that you would expect to have reasonable hierarchical structure, and it finds it. So the question is then going on to other pieces, and they do that, you know, they look at some, so this is E. coli, same kind of business. So a lot of these things kind of work reasonably well. It becomes a question of speed. They're all doing the same thing, right, which is hierarchical clustering. I'll show you one more of those in the next piece, and then we'll move on to some quite different approaches, right? So the link-based ones where there's overlap allowed, that's the sort of entry into moving away from pure hierarchies. And then one where you could have anything, kind of anything, lots of different structures. So, okay, let's have a break, and we'll come back for the rest of this business, all right?